So now let us take a look at exercise 1b, where we want to show that the mixed Poisson process has the order statistics property. And what do we mean by that? Well, according to the book, they say what you want to show is that given the knowledge that the mixed Poisson process attains the value n at time t. So given that, show that T1 up to Tn has the same distribution as an ordered sample of n IID uniformly distributed variables, which are each uniformly distributed on the interval 0 to t. Now we can show it this way. We can also show it a vaguely different way, which is actually the same way. We can also show it's because this is the same as saying that we want to show that the arrival times given n of t is equal to n has the same distribution as an IID standard uniform sample that has been ordered. And then after they have been ordered, we scale them up to the length of the interval 0 to t that we are looking at. So we can also write this instead. And the reason why I just did that quick explanation is because I think this is the version that you will see in the PDF solutions that will be uploaded online. So just so that you also have this. I mean, writing it up this way is exactly the same as the way we just wrote it up. They're equivalent definitions of the order statistics property. So whichever one you choose will work. Okay, so let's just show that n has the order statistics property. One way that we can do this is by showing that the probability that T1 is smaller than equal to some value, and so on, up to Tn being smaller than equal to some value xn, given that n of t is equal to n. So we can show that this thing has the same distribution function as this thing. Yes, so if they have the same distribution function, then it means that they have the same distribution, right? And let's just try to start from one end and see where we arrive. So first of all, the thing that annoys us the most when we consider something such as this thing here, or we have conditioned on n of t equal to n, is that there is one stochastic thing inside here that is kind of hard to work with. It's based on the fact that we know that the n of t is in fact defined as a standard homogeneous Poisson process with some random mixing variable that defines its intensity. I mean, basically, we should be able to look at this thing as a homogeneous Poisson process with intensity theta. However, we can only do that if theta is fixed, which it isn't, because it's a random variable. So the thing that we're going to do now is we're going to use what we call the tower property, and I'll just write it down here. So the tower property, what is that? Well, it is something we use whenever we have, we often use it anyways, whenever we have a function of, for example, two stochastic variables, and we want to figure out, for example, what this is. So what's the conditional expectation of g of y comma z given y? Now, one way we can do that, according to the tower property, is that I can always condition on something more. So I can condition on y and on z. And then afterwards I can say, I'll take this entire thing and plop it into one more conditional expectation where I only condition on y. So the tower property more or less allows us to fill in more variables that we want to condition on. And Uh, and this is very nice for us, because in our case, the thing that makes us confused is that we have a theta somewhere, right? So we want to be able to condition on that theta as well. So let's just try to do that. Here, the Tower property says, I mean, it's easier if we consider this probability as a mean value. So let's just do that first. So we have the mean value of an indicator function. That's the same as looking at the probability of an event, right? So the mean value of the indicator, that t1 is smaller than or equal to x1, and so on, until tn that's smaller or equal to xn, given n of t is equal to n. So basically what I want to do is I want to move the condition that n of t is equal to n outside in an outer conditional expectation, and then in the inner conditional expectation, I would like to condition on two things. I would like to condition on theta and on n of t being equal to n. And this works out because of the Tower property that I'm using in the same way as we wrote it up out here on the side. So let me just write the inner conditional expectation back into a probability, a conditional probability. So it's the probability of this, and all the way up to tn being smaller than xn, condition on theta and n of t equal to n, right? Given n of t is equal to n outside here. So now let us just take a look at whatever we have inside here. And notice that, well, given theta, the TIs will act like arrival times for a standard, for a homogeneous Poisson process with, well, we can consider it fixed intensity theta, so with the value theta. So this will then satisfy the order statistics property. Hence, we can apply the order statistics property to conclude that thing up there. So given theta, the distribution of the TIs, given that n of t is equal to n, is according to the order statistics property for just traditional homogeneous Poisson processes. It is given as the ordered sample of IID standard uniformly distributed variables u1 up to un as such. And I cannot forget that I still have to condition on theta, because it is given theta that such a relation holds. And on the outside, I also condition on n of t being equal to n. Okay, so what do I have now? Well, note that the ui, they are all uniformly standard uniformly distributed. They are IID, and also in particular, ui is independent from n. Hence, and also ui is independent from theta. So conditioning on theta doesn't make any difference for the probability distribution of whatever I have in here, right? So I can remove the condition on theta due to independence. And also, we note that since we have that the u's are all independent from n as well, we can also remove the condition on the n of t. And now I just have the mean value, sorry, this is not correction, the mean value of a probability, which is just a number. So the mean value of a number is just that number itself. And now we are done with this, because now I have shown that the probability that the distribution function of t1 up to tn, given that n of t is equal to n, well, is the same as the distribution function of n ordered standard uniform ID random variables, each scaled up to size t. So that was the order statistics property for the mixed Poisson process, which it has in common with the traditional Poisson process.